All right, welcome to our next module where we'll be essentially finishing up chapter 3. And the first thing we're going to look at is 3.4, which is a shorter section, but it still's got some quirks to it, but it's not too bad. All right, let's go ahead and get started. So last module, we talked about using synthetic division to kind of try to maybe divide something like this by some sort of factor or some sort of potential root. Now the idea here is the goal is to determine all roots of a polynomial. That's the main chapter goal. However, we aren't going to be able to find all the roots easily all the time, but one easy way is by using what we call the rational root theorem. And here's the idea, and it is simply that any rational root to the, I'm going to say above polynomial, and we'll discuss what's going on there. I'm also going to abbreviate polynomial, must be in the list of all factors of Q divided by all factors of P and positive or negative. Now, in other words, or rather before we dive in and explain what this is saying in one example, and notice in this example, we're not going to say what are all the roots. We're just going to identify the potential roots based on this theorem. And also, I really, I guess, should have said list all the potential rational roots. And then you might be wondering, well, what is a non-rational root? And we have discussed those. Those are when you need the quadratic formula, but the square root didn't go away. So this is saying all the ones where the square root would have worked out, how can you find them? Now, what's also included when you say the word rational is that means rational means ratio. Ratio comes from fractions. So what we're saying here is it is possible to have a root that is a fractional value. I'll tell you in this course we won't necessarily see that, but that does definitely occur. So, anywho, we're looking for all potential roots. Namely, we're not saying that all of these in the list will be roots. Well, literally because there's not enough room probably for all of them to be roots. What I mean by that is factors of 3 and factors of 6, when we put all them together, there's going to be way more options than 3, which again is, as we hinted at last time, the number of roots we know we have. Because this is to the third degree, there are 3 roots. Now they might be rational, or they might be irrational, aka you needed to square root the quadratic formula to get the last few, or they might be imaginary because you used the quadratic formula and you had a negative in your square root. Again, those are all big terms and not our total concern, but I just want to say that because it's all shown up in the scope of what we covered so far. Anyways, let's show you how easy this first question is to make you feel a little better about that. Now, what's this saying up here? It's saying the first and highest degree term, aka how you look at end behavior, the first term, that coefficient is what we're calling P. And then the very last term is the one we're going to call just Q. And so when we look at the factors of 6 and we look at all the factors of P, well, let's list those out. P is 6. We'll say that Q, sorry. Now I'm starting to think, oh, you know what? I'll correct this in the PDF. Q should be here. P should be here. I flipped these. You're just going to see it differently in your book. I mean, we could technically just be fine with this. There we go. All right, sorry. So, yeah, like I was saying, P is 6. Once I had the muscle memory of writing that down, I said, wait, they're in the wrong order. All right, there we go. So P is 6, Q is 3. Now, what are those factors? Well, the factors of 6, what multiplies to get you 6, could either be 1 and 6, or it could be 2 and 3. And well, 2 and 3 are right next to each other, so I've exhausted my options there. 3 is a lot less factorable. There's just 1 and 3. So what does it look like to make, catch this, the list of all values of p divided by all factors of q, and they could be positive or negative? Well, it actually is going to take a little bit to write, but we'll write it like this. P over Q could be plus or minus. Now here we go. 1 divided by 1. That's the first factor of P divided by the first factor of Q. And I'm going to go by cycling through all the P's first and then all the Q's. So then there's 2 over 1. Well, 2 over 1 is just 2. Then there's 3 over 1. Well, that's just 3. Then there's 6 over 1. Well, that's just 6. Then now I'm done putting all of these over 1, and now I'm going to put all them over 3. So 1 over 3, like I said, there could be fractions. 1/3. 2 over 3 is 2/3. Don't forget the plus minus. And then catch this, 3 over 3 is 1, but I've already written it, so I don't need to write it again. And lastly, 6 over 3 is 2, and I've already written that, so I don't need to write it again. So I guess I didn't need that last comma. And this would be your list. And as you can see, again, there's way more than 3 values here. There's actually 1, 2, 3, 4, 5, 6, and plus or minus, so a total of 12 different potential rational roots for this polynomial. Now, which ones work? Well, that's kind of the bummer, is you still have to do synthetic division, but the idea is, what we're about to do in the next example, is we're no longer being told what to put in synthetic division. We're being told, try all of these, and as you find what works, continue further. So now let's look at our next example. All right, for our next example, um, let's see here. We've got the factors of 18, and Q's just 1. So really, our P over Q list is going to be pretty simple. It's just all the factors of 18. Well, again, there's 1 and 18. I'll start writing my plus and minuses on them. There's 2 and 9. And there's 3 and 6. All right, those are all the ones that I should try. Now, we're not going to be crazy inventive here. We're going to try doing synthetic division with all of these until we find one that works. But we're not going to, do anything crazy. We're going to try positive 1, negative 1, positive 2, negative 2. I find it's better to just kind of go in order. So let's try positive 1. And let's also then write down our coefficients. Our coefficients are 1, negative 2, negative 9, 18. I'll go ahead and tell you, you're definitely going to want a pencil because we're going to try one, and if it doesn't work, I'm not going to draw a new one of these somewhere else. I'm just going to erase what I did and try again, and make a mental note to myself that I've tried positive 1, it didn't work, don't try it again. So synthetic division, as we learned last time, drop the first value. Now we multiply. Now we combine. Oops. And now we multiply. And now we combine. And I can already tell that that's not going to work out because negative 10 here isn't going to make 0. So now I know that positive 1 is not a factor. I'm going to erase my work. And now what am I going to do? Well, I'm going to try negative 1. So let's try negative 1. Drop that down, multiply it. That's negative 1. Now I get negative 3. Multiply, that's positive 3. Combine, that's negative 6. Multiply, that's positive 6. Again, I can tell that that's not going to end up being 0. So guess what? I'm wrong again. And if you're sitting there going, wow, this is a tedious process, you're not wrong, but we are eliminating options, so that's good. We're making progress in some sense, it just doesn't feel like it. Let's just keep going until we find one. I don't have this pre-worked out because again, I kind of don't believe in that. If I can't do it with you live, then there's no point of assessing you on it. All right, so I tried 2, and that got me 2. I combine, this is interesting, and I get 0. Now, we've seen zeros in synthetic division before, or we've had to put in zeros, but we've never gotten zeros, I don't think, together in our work, so this might be interesting. Yep, multiplying by 0 gives me 0. Dropping that down gives me -9. And ooh, look at this. Multiplying this gives me -18. And now I get 0 as my remainder. Now this is very interesting because we've now found our first root. 2 is evidently a root. Now, what are we left with? That's very interesting. What I'm left with is, remember, from the remainder, there's a number, a thing with an x, and a thing with an x squared. It just keeps on increasing. If there were more terms, it would be number, x, x squared, x cubed, x to the fourth, on and on and on. But we only got up to squared. Now, also, catch this, there was no x term, so this is what we have left over. Now, this takes us all the way back to our first review week where we said, hey, knowing how to factor trinomials or some of these special ones is important. This is what we call a difference of squares. It breaks down to its square rooted values. Now, in other words, let's think about it maybe in this context or in the regular factoring context. What can multiply to 9 but subtract to 0 because there's no sign in the middle? Well, oh, sorry, I wrote that wrong. I was thinking ahead. -3, +3. Well, what multiplies to 9 and subtracts to 0 is -3 and +3. Those subtract or combine because they're different signs. It'll be subtraction, but by combining and therefore subtracting, there's 0 in the middle, and then at the end, there's a -9 because one was positive, one was negative. And that means we found our second and third root, +3 and -3, in order as I saw them. So here's what I'm going to end this video with. That means for this question, way to catch this, the factored form would be of this entire polynomial, x minus 2, x minus 3, x plus 3. I mean, you can hopefully kind of see that because we already had the -3 plus 3 right here. But then I want to write down the roots, and I'm writing down the roots in order of their algebra. The roots are 2, 3, and -3 because each one of these makes their parentheses like correspondent 0, which multiplies through and makes the whole thing 0, which is why roots are again sometimes referred to as zeros. They make your polynomial or your algebra equal to 0 when you plug them in. So that's really interesting because this is the missing link between what we looked at for graphing and looking at, the factored forms and multiplicities. This is the missing link of how do you take a regular polynomial and get to where you could discuss multiplicities or turning around and end behavior, or I guess not end behavior, but turning around at the 0 or passing through the x-axis or crossing through the x-axis. It's by being able to factor, and you factor by breaking down using synthetic division until you can get to a x squared and factor like normal. Very interesting, and not an easy skill. And so I will say that even though this homework is short, you're going to spend a lot of time doing synthetic division. Kind of notice how we did that. We did 3 different rounds of this before we found 2, and then we still had factoring afterwards. Now, some of you, if you decided, to go through in a random order, you might have found +3 first. And although I'm trying to keep this video short, I think it's worth going through this example one more time. Now that we've done it, we know the answers. We know 2, 3, and -3. But I want to show you that you can get your answers in a different order, but it's all fine. So I want to approach this problem again, and sorry, I am just pulling out a separate new sheet of paper. But let's say that for some reason, and I mean, I wouldn't blame you, because it's not always fun to just do 1 and -1, 2, -2. You might just think, you know what? I'm going to go with 3. So let's see what happens if you choose 3 as your potential first root. We get 1, we multiply, we get 3. We get 1, we multiply, we get 3. We get -6, we multiply, we get -18. And that gives us 0. And that should not surprise us at all because after all, we already know that 3 is definitely a root. Now this time I found it first though, and so look at what happens here. I now have a new set of algebra, but that new set of algebra still translates to a regular 3-term structure that I can factor. What are the factors of 6 that subtract to 1? Well, the factors of 6 that subtract to 1 are 2 and 3, which again should sound familiar. But what signs do these need? Well, in order to subtract to positive 1, if we think about foiling this out, the 3 is going to need to be positive and the 2 is going to need to be negative because, again, a positive 3 and a negative 2 leave you with positive 1 in the middle, but a negative 2 times a positive 3 gives you negative 6 at the end. And so look, I found my first root, which is 3, and what makes each of these equal 0? Positive 2, and then negative 3. And so at the end of the day, what we've said is we've said 3, negative 3, and 2. And here we said 2, 3, and negative 3. It's the same roots, we got them in a different order. And if you're sitting there going, that's crazy, how is that possible? Here's the last thing we'll say, and then we're done. Let's just look at factoring regular numbers again, like 30. There's a way of factoring called prime factoring, where you break every number down into its smallest prime factors. Now, primes are 2, 3, 5, and so on. Any number, I guess when I say so on, it's any number that's only divisible by 1 or itself. Or I should say 1 and itself, and that's why the first prime number is 2, not 1. Anyways, what do I mean by that? Well, let's look at 30. How could I break down 30? You might look at 30 and go, ah, yes, 3 and 10. Now, 3 is prime, but 10 is not. So how do we break 10 down? 2 and 5. And so, great, I now have my prime factors. That's how I can make 30. But someone else could say, oh, I know 30. 30 is 2 and 15. And 2 is prime, but 15 isn't. There's 3 and 5 left over. Oops, 3 and 5 left over. And so this idea is exactly what just happened in our synthetic division. At the end of the day, we get 2, 3, and 5, and yes, I did choose the number that gives us 352 because we're in Ocala. You're welcome. But the bigger idea here is that no matter what, we get the same 3 prime factors, but we can get them in different orders, and also our second problem, our second sub problem, so to speak, is definitely going to look different if you choose a different first factor. So again, notice when we chose 2, we got this difference of squares and still factored. But when I chose 3, I got a totally different quadratic, but it still gave me the other 2 roots. So why am I over-explaining all this? Because I just don't want you to be afraid that if someone says, oh, I tried 2 and it worked, or I tried 3 and it worked, don't think that because you don't go in the same order as everyone else, that you're not going to arrive at the same final conclusion. You will, as long as you factor correctly, you do your synthetic division correctly, and you don't continue on and try to factor until you get 0 as your last term. If you don't get 0, you got to erase and try a different number. All right, I'll see you for 3.5.